Okay, so let's talk about sound. Well, first thing we're going to talk about here is we want to look at the nature of sound signals, and that means that we are going to need to understand waves and different ways to compute information that we can pull from waves. So first, what is a sound? Well, a sound is the propagation of a pressure wave in space and time through a medium with compressible molecules. There's a lot to unpack there, right? So a wave, specifically a pressure wave, we'll talk about a pressure wave in a second, but a wave is something moving through something else. You can think about it like an ocean wave, although in a few seconds I'm going to tell you how a sound wave is different from an ocean wave, but think about it right now like an ocean wave. So an ocean wave is moving through the body of water that it's on. Well, it doesn't have to be an ocean wave. It could be a wave in a lake. If you have a fan near your bathtub, you can even get waves on your bathtub, right? But that wave, that water wave, is moving through a medium. And it's moving in space and time. What that means is moving through space, it's traveling across the surface of the water, and it's changing over time, right? It's not staying in the same place. That kind of makes sense. It makes a lot of sense that it's changing in time and space. The medium, again, is in this case the surface of the water. Waves don't actually, carry through to the bottom of the ocean until they hit like a continental shelf, and then they start to become those waves that lap all the way up onto the beach and then pull back. But out in the ocean or in your bathtub or whatever, they don't reach all the way down. It's not like the water is rushing all in one direction together. It's really just what's going on at the top. All right, so sound is a pressure wave in space and time through a medium, right? So in our case, in speech, in the typical speech sense, like the way you're listening to me now, it's a pressure wave traveling through air, and that's how it ends up reaching your ear. The essential elements of sound that we have to have are a sound source, one, which in my case are my vocal folds, creating that buzzing sound that you should remember from anatomy and physiology. It's being shaped by my articulators, and so then you could think of me as the sound source, you can think of my vocal folds as the sound source. It depends on how you want to parse that down. But I'm producing sound, and then it has to have a medium to travel through as well. Now, sound does travel through all sorts of mediums. It can travel through gases, liquids, and solids. And this graph right here shows you the speed through different mediums. So you can see that air, it's actually a lot slower in air than it is in these other mediums as well. That's true. Sound underwater travels almost 4 times faster than sound in the air. You can see that through petroleum, it's a lot faster than in the air. Through the human body, it's a lot faster than in the air. And then through solids like iron and aluminum, it's even faster than through those liquids like petroleum or, I guess, blood and other goop. And that's why if you think about, I don't know, this might be a really dated reference, but in old Western movies, people would put their ear down on the train tracks and try to hear if there was a train coming. And the reason for that is sound travels well through a solid like iron or steel train tracks. It travels quickly, and also it doesn't fall prey to dying out like it does in the air, like sound waves do in the air. We'll talk about why that happens much further on in the class, but essentially, any medium is necessary. And that's why, if you're a fan of 80s sci-fi movies, which I definitely am, you'll know that in space, no one can hear you scream. It's from Alien. But that's true. The reason why sound can't travel in space is there is nothing in space, right? There's nothing for sound to push against. There's no medium for the sound wave to push against to propagate the sound wave. So sound can be created. There can be a sound source in space. Maybe not me, because I'd die because there's no air. But like, let's say we took my guitar out, and here, this is a pretty science fiction noise. So we could do that in space. I could do, somebody in a spacesuit could do this. Me, I guess. You could make that noise. You'd have the sound source, but without the medium, there's no sound. These just vibrate, and there's no particles for them to push against, which means that those particles that they're pushing against can't push against other particles, and it can't reach anyone's ear or any microphone or anything. So I could have the microphone right next to it, right there, right at the very top of the guitar, and it wouldn't pick anything up because there's no medium. So we need a sound source and we need a medium. All right, well, sound sources are vibrating bodies, right? That's just true all the time. So a sound source needs to be able to vibrate. It also needs to have mass and elasticity. So you can see this tuning fork right here. I don't know, tuning forks, I mean, like when I was in school, people would bring them out every once in a while. Sorry. It's a Slack message, so if you use Slack, you can look forward to that kind of stuff. Well, I mean, anyway, it's not like messages are going to pop up unless you have them set to pop up. Anyway, when I was in school, and I mean like grade school, high school kind of thing, people would whip out tuning forks every once in a while. I'm not sure if that's still a thing that anyone has outside of somebody who deals with sound. I don't have my own set of tuning forks, but I would love to get some. And because of that, I want to show you what a tuning fork does. Also, this music that they're going to play is just ridiculous. I want to start every video that I have like this.
Amplify your lessons on waves and sound with these terrific demonstrations using tuning forks. The sound from a vibrating tuning fork isn't audible all the way across a classroom, so you can increase the amplitude by touching one of the tines to the edge of a piece of paper or plastic dish. Show students that the tines are vibrating by lightly touching the fork to a ping pong ball hanging from a string. Demonstrate that the vibrating tuning fork sets the adjacent air molecules in motion with a cup covered with plastic and pepper sprinkled on top. And it's always fun to dip a vibrating fork in a cup of water. Try a different frequency to see which makes the bigger splash. Use a stroboscope to create the illusion that the tines are moving slowly, and students will see just how far they oscillate. Combine science and music by creating a C major chord. With these demonstrations, your students will really get in tune with the concepts of waves and sound energy.
Okay, so those are tuning forks. They're amazing. Again, at some point I might get my own, and I'll make a video about it. Anyway, what's important about a tuning fork is as soon as you hit it against the surface, it starts vibrating. The vibrating motion of those two tines creates the sound that you really couldn't hear in that video, but it creates something really close to a pure tone. A pure tone, let me show you a pure tone. So a pure tone, this is Audacity, by the way, which if you choose to use this, you'll see this again. If we go to Generate and Tone, you can generate any sine wave or square wave, sawtooth wave, or whatever. So I want to show you a sine wave. 500 hertz sine wave for, let's do it for 1 second. Ba-bam. And this is what a sine wave sounds like. Hopefully that was loud enough for you to hear. If it wasn't, I'll maybe edit it into the video. Oh, I can make it louder. That was set way too loud and it didn't actually sound like a sine wave. There we go. And now one other thing I want to do really quickly before I move back to the slideshow is I want to zoom in on this so you can see what the wave actually looks like. If we zoom in, you can see that it looks like this nice little sloping wave. You're going to see this again a lot in this class. This is what a sine wave looks like, and this is kind of our basis for studying all of sound. We look at the sine wave. A sine wave is called a pure tone because we assume that this is the fundamental way that sound would be represented. I mean, if you could break any complex sound down into its most basic part, it would be a pure tone sine wave. It's hard to do that because everything has harmonics and everything vibrates other things around them, so you have sympathetic vibration. We never quite get a perfect pure tone sine wave, but this is what we're looking for. And in the next lecture, you're also going to hear about something called Fourier. Is that the next one or is that the third one? Well, you're going to hear about Fourier transform. Fourier transform essentially takes any complex tone and tries to break it down into its component sine waves, because every complex tone is made up of numerous sine waves acting together. So anyway, what you're going to see a lot of when we talk about sound is the most basic forms. We can kind of understand what's going on without the noise of a complex tone. That is until we start working with complex tones, and then we'll just talk about complex tones. But anyway, this is a sine wave. Okay. So, a sound source needs to vibrate. It also needs to have mass. The reason it needs to have mass is because if you don't have mass, it's not actually going to be able to vibrate. It needs to have elasticity. We'll talk about that in a second. Mass is the amount of matter present in the object, and you can calculate density from that by taking mass divided by volume. So you can have, this is just your typical physics principle, right? You can have a little chunk of brass, or you can have a little chunk of paper, cardboard, and one is more dense because there's a lot more mass per volume in the brass than there is in the cardboard. So we would say that the brass is more dense. The more dense the object, the quicker the sound is able to travel through that. And if you think back to this graph, which you don't even have to think back about because here it is, you can see that as density increases, the speed of sound increases. So air is not very dense. We can move through it with ease. It's hard to move through a human body, so that's definitely more dense than air. And then it's really hard to move through iron because that's more dense than a human body and air. So you can see that there's a relationship between the density and the speed of sound that moves through it. All right, elasticity. That just means that, well, okay, sorry, let me start over. Matter is going to change shape when it gets pushed on, right? So you can think about Play-Doh. You can push on it and it changes its shape. Play-Doh doesn't have a lot of elasticity though because it doesn't rebound. It doesn't try to oppose your force and it doesn't try to pop back when you push on it. Now this little thing right here, this is showing molecules of something. This could be maybe a solid, maybe iron or maybe molecules of water. So it doesn't really matter. But the elasticity inside is going to oppose the deformation. It's also going to allow the matter to return to its original shape after it's been deformed. So you can see that right here, everything gets pushed in, then it pops back out. It gets pushed back in, it pops back out. You can think about this. This is why I have the guitar. So a guitar string is stretched when you pick it or pluck it or do whatever, right? So if you can see that I'm putting pressure on this right here. and then I let it go, and I created a terrible sound because I hit multiple chords at once. Let's do that again. We'll do it without the pick, I guess. So I'm going to pull the string. You can see that I'm deforming it, and the elasticity wants to pull it back into its spot. So what's happening, the reason why it continues to vibrate, is you can think about this mass spring right here. This is called a mass spring model. It's a really easy name to, well, probably for them to come up with, because it's a spring with a mass on the end of it. Like, whoop-de-doo, guys. But it's okay, because it's easy for us to remember, too. So what's going on there is, if you had the spring all the way compressed, at its resting state, and you put a mass on the end of it, it would fall, but then the spring would pull it back up, and then the mass would fall again, and the spring would pull it back up, and the mass would fall again, and the spring would pull it back up. Unlike this GIF that I have on the PowerPoint, it's not just going to do it for the rest of time, right? It's going to do it for a while and kind of dampen out. But what happens is there is an equilibrium point. From anatomy and physiology, you might remember equilibrium points for breathing, like where your lungs and your diaphragm want to be at rest. So there's an equilibrium point for this mass spring model. Let's say it's right here. So I attach the mass, and it's going to go beyond, and then it's going to come back up because now the spring has been stretched, and it's going to come back up. Now we're beyond again. The mass pulls it back down again, it comes back up, and then eventually it reaches this equilibrium point. But before it gets to the equilibrium point, it vibrates around the equilibrium point, just like my string wants to do. I pull it out to the, I don't know, what direction is this for you guys? This makes me wonder if my video is flipped. I'm pulling it out this way to my right arm, my right hand. So I'm pulling it out to my right, and I let it go. And what happens is it goes way past equilibrium to the left, and then back to the right, back to the left, back to the right, back to the left. And I can still hear it vibrating a little. It's dampening itself out. It's about pretty much done now. And so it's gotten back to its equilibrium point. Okay, so vocal folds are also, if you remember from anatomy and physiology, something that vibrates to make sound. So vocal folds are stretched as puffs of air push them apart, right? So imagine my two fingers here. Let's go this way. Imagine my two fingers here are the vocal folds. A puff of air from back here is going to blow them apart. They're adducted right here, very tightly. So when that puff of air pushes them apart, like that, they're being stretched. They're being stretched out of their equilibrium state, where they want to be, right? Boom. So they're going to come back closed. And then air is going to build up behind again, and then it's going to blow them apart, and then you're going to get this kind of chopping motion with little puffs of air that come out. And that's the vocal folds as well. So they have elasticity. They want to come back together, and they're going to then vibrate to create sound. All right. So let's talk about waves now. We've got a couple different types of waves. Yeah, okay. Obviously, I reused that slide. So we've got a couple different kinds of waves. The first is a longitudinal wave. If you think about longitudinal, well, I don't know if you're going to know this, but a longitudinal research study is one that goes from birth until old age, because you're going along the lifespan of the person. And that's that might help you remember a longitudinal wave as well. The particles, so now let's think about it like air. The air molecules are going to vibrate in the direction of the wave, right? So out of my voice coming to you, the air is going to be pushed forward at you. And the particles are going to move in that direction too. They're not going to move with the wave. I mean, they are going to move with the wave, but they don't travel the entire duration of the wave. Like these air molecules aren't traveling from my mouth to my camera microphone, and then a new set of them aren't traveling from your speakers into your ear. That's not what's happening. The particles are kind of rebounding in their area, but they're moving in the direction that the wave is moving. That's a longitudinal wave. And this one right here, this shows you a longitudinal wave. These slides, by the way, are up on PowerPoint, are up on Canvas in PowerPoint form. So all of the GIFs and everything will work for you if you want to take a look at it. You can also make them bigger if you want to see any of these images larger. So this right here, this is a longitudinal wave, and you can see that you get these like bands of compressed molecules, right? So as this plate right here pushes the air together, here, let's wait for it. There we go, boom. So it pushes these molecules together. Now they're going to rebound back to where they were, but then that front, that wave front, is going to push more molecules together, and then they're going to rebound. So you do get a wave of compression, and then the parts where it's not compressed is called rarefaction, that is going to travel in a direction. The particles are going to travel in that direction as well, but they're not going to stick with the wave for the entire duration of the wave. A transverse wave, this is how light moves. A transverse wave, and this is also this right here. The transverse wave, the particle is going to move in the opposite, not the opposite direction, sorry, in a perpendicular direction to the direction that the wave is moving. So in this image right here, the wave is moving this way, towards the words. The particle is actually not moving in that direction at all. The particle is moving up and down, right? So the wave is moving this way towards the words, like that, and this particle is moving just up and down. It's not displacing at all in the direction that the actual wave is moving. That's a transverse wave. Remember a transverse cut? That might help you with that too, a transverse section from anatomy and physiology. All right. Why do I have that? Okay. Let's talk about water before I hit this next bullet point. I got them out of order for some reason. Water that you can see right here, this is actually moving in a combination of the two. That's why I said earlier you can think about it like a water wave, but soon you're going to figure out that it's not quite the same. Water waves move in a combination of the two. There's a longitudinal wave and a transverse wave moving at the same time. So if you watch this one particle right here on the top of this water, it travels around this circle. And so what's happening is, yes, it's moving up and down because it'll go from the bottom of the circle to the top. That's which kind of wave? A transverse wave. And then it's also moving in the direction of the water because it goes from the left side of the circle to the right. And that is which kind of wave? Longitudinal. It's really weird to try to leave space for people to answer when you're not actually here. So you can see that they're doing the same thing. All right. So then I also wanted to mention that drum head, if any of you play drums, the actual head of the drum, so like the skin part, that moves with a transverse wave. So as soon as you hit the drum, boom, then ripples shoot out across the entire drum head from where the stick hit. It's going to ripple out like that. And that's going to be a transverse wave because the actual, because that wave is moving out to the sides of the drum, but the actual particles of the drum head are just moving up and down where they are. They're not leaving. What's interesting about a drum, though, is the air column inside the drum is a longitudinal wave. So you have this expansion across the drum head. That's a transverse wave. But then as the drum head is shaking, it is pushing on the air column inside the drum, and that creates a longitudinal wave, and that's what really creates the sound that we end up hearing. So there's both kind of going on there, one on the surface and one inside. And then water, both are going on at the same time. All right, so again, sound produces a longitudinal wave that travels through space. And you can see this is a really good example right here. these bands that you see right here, and this one that goes with wave, this is a band of compression. And you can see this right here. Let's wait for this to start over again. Boop. So we've got compression, rarefaction, and compression. So you're going to have an area of compression, an area of rarefaction, and another area of compression. Those individual particles do not travel with the wave forever. They move with it, but then they're going to rebound. So watch these individual little particles here. They get caught up with these other particles, but then they bounce back. And if you notice, they kind of zoom back a little quicker than they moved with the wave. So they're moving, and then they break off and they go. And you can see that all throughout here. And this is exactly what's happening in air when you listen to sound. The air isn't just like moving in an air current, you know, at you. Like this molecule is not going all the way to you, but the air is moving, and that is what creates the sound wave. All right. So we already talked about this, but anyway, where these air molecules are pushed together, that's compression, and that's going to have higher atmospheric pressure than the average surrounding where you are. Atmospheric pressure changes day to day, location to location, day to night. But when we talk about high and low pressures in terms of speech, that's just compared to the average if there was no sound happening, right? Speech or sound, either way. So relative to the atmospheric pressure in the room that I'm in, I'm going to speak, and then I'm going to have these areas of compression that have higher atmospheric pressure than average. And then behind those, in the rarefied areas, that's going to have lower than typical atmospheric pressure, and then you're going to have this area of higher atmospheric pressure. The reason that the particles, you know, one of the reasons that particles don't move with the wave as it goes is because this rarefied area, this area of low pressure, is going to, you know, it's kind of like a small vacuum behind it, and so it's going to pull molecules to like fill up that area again. And then when those come back together, you've got another front moving in, and then they're going to try to fill it back up, and then you've got another front of compression. So you get these alternating compression, rarefaction, compression, rarefaction. And that's really what helps propagate the wave through the air. This is true in liquid and solid as well. I think you can imagine that in liquid it's pretty much the same thing. You just got more molecules, you know, together. And so you get areas of more compressed fluid versus less compressed fluid. And in metal, say iron or steel, the same thing is happening. The molecules can move in there, but they don't move, say, as much. There's a lot more resistance to movement, but they're going to move and they're going to, you know, pop right back. So you'll get this kind of this area of high pressure that that the molecules inside the steel actually do push together in the same way that the molecules in the air do. They don't compress as much because they can't, otherwise the metal would break, and you know, sound isn't just going to break steel. But they do push together and allow the sound wave to propagate through the entire body of whatever metal thing you're looking at. All right, so I have pretty much said all of this already. I think I just wanted to give you a couple more examples of what's going on. So here you can see one sound wave front moving towards these molecules. You can see the compression wave move through, and then there's a rarefaction wave behind it. All these molecules are evenly spaced, and this one little green molecule gets caught up in it, and then it comes back. And you can see that it gets caught up and pushed forward with a whole bunch of molecules, and then there's kind of this little vacuum area behind of the rarefaction, and then it's going to jump back to where it was. You can also see down here the blue bar is showing pressure. Where there are more molecules, there's higher pressure, and then there's lower pressure in the rarefied area. I feel like in this example, the pressure is actually not where it should be. Pressure should be a little bit more forward. The peak of it should be where this big clump of particles are, because the more particles that are in one place, the higher the pressure is. So it's slightly misaligned, but at least it gives you the idea of what's actually happening. Okay, so let's look at this really quickly. I've rotated this graph, and you can see that this is time moving down this way. So if you're graphing this particle moving right here, you'll start at this time and it's going to move up and down. So you're going to start at time and then you're going to move with time and kind of track it. And so think of it like you put a pen in the particle and then you're pulling a piece of paper up at a constant rate. And that particle is just drawing a line on the piece of paper, right? And so it would end up looking like this. The particle is just moving back and forth in the direction that the sound is moving. And you're pulling at a constant rate. And so then you get this perfect little sine wave pattern, right? That's great. The amplitude, right here, you can see amplitude. This is going to be, this corresponds to how loud a sound is. So if this was a loud sound, you would expect the amplitude to be really large. The particle would move a lot more. If it was a quiet sound, the amplitude would be a lot less. So the particle would move a lot less. The rate that it's moving is dependent on the frequency. We'll talk about that in a second, but this is maybe, we'll say it's a moderate frequency. A higher frequency, the particle would move back and forth a lot faster. A lower frequency, it would move back and forth a lot more slowly. So the frequency has nothing to do with the intensity or the amplitude. So the loudness of a sound has nothing to do with the frequency. We do know that they're correlated in a lot of like biological entities, like humans and animals, and even some just instruments. So there's some physical reason why intensity and frequency might be correlated, but they don't have to be. Just being correlated doesn't mean they always go together. So know that the amplitude is just loudness, how much the particle is actually moving, and that's independent of how fast it's moving back and forth. So it can move just this much really quickly. That would be a soft, a quiet, high-frequency sound. Or it can move this far really slowly, and that would be a very loud, low-frequency sound. So you can have that. All right. This is, again, kind of another idea of what's going on here. So this is showing time again on this axis right here, and this is the amplitude or the displacement of the particle. So you can see that as it moves, the particle isn't moving in this case. So this, think about what kind of wave this is. It's a transverse wave, but the properties of it are similar when we're measuring them. So it's going to move up and down. This particle is going to move up and down, and the rate that it moves up and down is going to tell us something about the frequency. You can measure that also. You can look at position. So this is taking a snapshot at 27 seconds. So this lets it go for a time, and then at 27 seconds it wants to look at the position of where particles are in this space. And it's going to notice that some of them are down and some of them are up, and some of them are down and some of them are up. And so that's another way to look at it too. So this is at one time, and this is at one place. So we're holding one of those constant. When we look at it at one place, this graph needs to change like this over time. And when we look at it at one time, then we have to measure different places along, an area of air or water or whatever. All right, so let's actually talk about measuring something. So waves, as you know, they're going to vary across space and time. The frequency of the signal, how high or low the sound is the rate that the sound wave is going to be repeated over a particular period of time. Usually we use 1 second. Cycles per second is hertz is cycles per second, and most of the time we're going to measure frequency in hertz. All of the time in this class we're going to measure frequency in hertz, which is going to be how many times the sound is repeated in 1 second. But of course it doesn't necessarily have to be. So what you've got here is you're going to measure the wave from, it's a little dicey because you could fall into a trap of measuring it incorrectly, and I'll show you why. So you can measure it where it crosses the 0 line right here to where it crosses the next 0 line in the identical place. That's important. So see here, it's crossing the 0 line. The wave crosses the 0 line here too, but that is not an identical place on the wave. Here the wave is starting to move up. Here the wave is starting to move down. So if you're going to measure the one complete cycle of the wave, you need to go from where the wave starts to move up to where the wave starts to move up. So from here to here, that is actually measuring the wave. You can also do it from peak to peak. So you can go from here to here. You can go from trough to trough. You can go from here to here. Those are acceptable. And you can, again, you can go from 0 crossing to 0 crossing, but you have to be mindful that you are not measuring the 0 crossing when it's going down, when you should be measuring going up. So you could measure from wave starting down to wave starting down, wave starting up to wave starting up, and then again peak to peak, trough to trough. These are all ways to measure the wave. Great. So if you had this laid out in, you know what, I think I have that on the next slide. I do. Oh darn. I was hoping that this wasn't moving. But it stops every once in a while, so that's good. So each of the space between each of these little reddish brown bars is 1 second. So how long does it take in time to repeat the wave again? If you count from peak to peak, it's going to go here to here. So it's going to go 1, 2, 3, 4. This is hard to do. You're going to go through 4 of these, right? So if this is T0, which is where this would be starting, you'd have 1 second, 2 second, 3 second, 4 second, right there. Timed perfectly. Okay, so it's going to take 0.4 sorry, I wrote this incorrectly. We should say 0.1 second here, because when you count all 4 of them up, it's 0.4 seconds. I'm screwing up my own math. Sorry about that. So if these are all 0.1 second, then when you count them all up, it takes 4 of them to go for 1 full cycle of the wave. So it takes 0.4 seconds for the wave to complete 1 cycle. The formula to find the frequency is frequency equals 1 over t, the time that it takes to complete 1 cycle. That's t. So t equals 0.4 seconds, then frequency is going to equal 1 divided by 0.4, and 1 divided by 0.4 is 2.5. And that means that the frequency of this wave right here is 2.5 hertz. Remember, hertz is cycles per second. All right. Wavelength is going to be the actual distance that the wave travels in 1 repetition of the wave, like the actual space covered by 1 repetition of the wave. So where 1, frequency, you're going to start with a measurement of time. How long does it take for the cycle to repeat itself? Wavelength is going to, so frequency is a measure of the time it takes to complete 1 cycle of the wave. Wavelength is actually looking at how much distance is covered by 1 cycle of the wave. So that's how they're a little bit different. Frequency, I guess I should point this out to you. Frequency is denoted by an F. These should have been, oh man, these should be italicized. Frequency is denoted by a lowercase italicized f. T is denoted by a lowercase italicized t. Wavelength is denoted by the Greek letter lambda. All right. So there is an inverse relationship between wavelength and frequency. All that means is the longer a distance it takes, so let's say it takes 1 foot. No, that's going to be hard to do. Let's say it takes 100 inches for one cycle to repeat. That means it's going to be a very low frequency. 100 inches is really long, and so that means it takes a lot of time to travel that distance. So 1 over the time it takes for the cycle to complete is going to be a very low frequency. It's going to be like way subsonic, you know, like 0.2 hertz or something like that. Very low, inaudible to humans. But if you have one that takes, you know, instead of 100 inches, it takes 10 inches to cover, that's a lot smaller of an area. And then you're looking at a much higher frequency because you're packing one entire cycle into a much smaller area. So boop, that's going to be a lot higher than something that goes boop like that. So inverse relationship between frequency and wavelength. The longer a wave is, the lower a wave is. The shorter a wave is, the higher the wave is. So little number in distance is higher number in frequency. Big number in distance is little number in frequency. The relationship is right here. You've got lambda, which is your wavelength, equals c divided by frequency. C is just the speed of sound in air. But you can see that there's an inverse relationship here. As f increases, lambda decreases. All right. And that is the end of this lesson. So these are the things we took a look at. And you're going to be using these, well, you're going to be using them in the knowledge check. I'm going to have you compute the frequency of something. And then we're going to build on these throughout the rest of the videos. And then by the end, you're actually going to be doing these kinds of things with a program. So you're going to use a program to calculate the frequency of something. But this is how you would do it by hand, which you won't, in practice, really be doing a whole lot. You know, once you move into the workforce, you won't be doing that. But of course, just like with math, we make you do it by hand first, and then you get the calculators and things. Oh, by the way, you can absolutely use a calculator for the knowledge checks, for the quizzes, and for the exams. I told the respondus people that a calculator is totally acceptable to have with you when they do the room check. So it's simple math. All of you will be able to do it, you know, in your head, probably without even a piece of paper. But I always feel better having a calculator, so I'm letting you use the calculator as well. Okay, great. See you in the next video.